Picture a nuclear-powered missile the size of a railroad locomotive screaming across the landscape at 3 times the speed of sound, spewing radioactive exhaust, and carrying 26 thermonuclear warheads with enough firepower to end civilization as we know it. This isn't science fiction, it's the terrifying reality of SLAM, a weapon so horrifying that even Cold War military planners eventually backed away from it. The most chilling part? Its nuclear reactor was actually ground-tested successfully, proving the technology worked. Today, as global tensions reach levels not seen since the 1960s and hypersonic weapons dominate headlines, we need to revisit this nightmare machine that nearly became operational. But to understand how such a monstrous weapon could even be conceived, we must first examine the desperate circumstances that drove its creation. The nuclear delivery crisis of the 1950s. By the mid-1950s, military planners on both sides of the Iron Curtain faced a stark reality that threatened to undermine the entire nuclear deterrent strategy. The atomic weapons they had spent billions developing were useless if they couldn't reliably reach their targets. The bomber aircraft tasked with carrying these weapons across the vast distances between hostile nations were becoming sitting ducks in an increasingly dangerous sky. The Boeing B-47 Stratojet required 10 to 12 hours to reach targets deep inside the Soviet Union, giving enemy defenses ample time to prepare. These aircraft faced the growing threat of sophisticated surface-to-air missile systems like the Soviet SA-2 guideline, which could engage targets at altitudes up to 25 kilometers. Both superpowers had deployed similar SAM systems by the mid-1950s, transforming what had once been a theoretical threat into a practical certainty that most bombers would never reach their destinations. Fighter interceptors posed an even more immediate danger. The Soviet MiG-19 and MiG-21 fighters could climb to bomber altitudes in minutes, while American F-101 Voodoos and F-102 Delta Daggers offered similar performance. These aircraft carried air-to-air missiles specifically designed to destroy large bombers. Intelligence estimates suggested that conventional bomber formations would suffer casualty rates exceeding 80% against prepared defenses. Military leaders recognized that speed alone might solve the penetration problem. The Convair B-58 Hustler achieved supersonic speeds, but carried a limited payload over short distances. The ambitious North American XB-70 Valkyrie program promised Mach 3 performance at extreme altitudes, but its enormous size and heat signature made it visible to radar systems hundreds of kilometers away. Even at 3 times the speed of sound, these aircraft still required hours to reach distant targets. The Soviets pursued similar approaches with the Myasishchev M50 Bounder and Tupolev Tu-22 Blinder programs. These aircraft incorporated advanced materials and propulsion systems, but faced the same fundamental limitations. High-speed flight consumed enormous amounts of fuel, reducing range and payload capacity. The faster these bombers flew, the more vulnerable they became to detection and interception. Range limitations created additional strategic vulnerabilities. Bombers needed forward bases to reach targets across intercontinental distances. These bases became obvious targets for preemptive strikes. The Strategic Air Command attempted to address this problem through continuous airborne alert missions, but even these operations left crews fatigued within 24 hours, underscoring the fundamental endurance limitations of conventional aircraft. The missile age promised to solve some of these problems, but created new ones. Early intercontinental ballistic missiles, like the Atlas, required hours of preparation before launch and used liquid fuels that couldn't be stored indefinitely. The missiles themselves were accurate enough to hit cities, but lacked the precision for military targets. This limitation forced planners to rely on enormous warheads that created unacceptable collateral damage. Submarine-launched ballistic missiles offered better survivability, but faced severe payload and range restrictions. The Polaris missile system under development could deliver warheads across 2,000 kilometers, but carried relatively small nuclear weapons. The submarines themselves moved slowly and required weeks to reach launch positions. These systems complemented rather than replaced the bomber force. By 1956, the strategic situation had reached a crisis point. traditional bombers were becoming obsolete faster than replacements could be developed, ballistic missiles remained years away from operational deployment in meaningful numbers. The gap between obsolete delivery systems and future capabilities threatened to leave both superpowers vulnerable to surprise attacks. This crisis of capability drove military planners to consider increasingly radical solutions. If conventional aircraft couldn't penetrate modern defenses, perhaps unconventional approaches might succeed. The concept of nuclear-powered flight had existed since the early 1950s, but had been dismissed as impractical due to shielding requirements. Manned aircraft needed heavy radiation shielding to protect crews, making them too heavy to carry meaningful payloads. The solution emerged from a simple but revolutionary insight. An unmanned nuclear-powered missile would eliminate the crew protection problem entirely. Without the need for biological shielding, designers could dedicate the entire aircraft to fuel, propulsion, and weapons. Nuclear propulsion offered virtually unlimited range and endurance, allowing missiles to remain airborne for days or weeks if necessary. This approach promised to solve multiple problems simultaneously. Nuclear-powered missiles could fly at low altitudes to avoid radar detection, eliminating the need for extreme speed. They could loiter over the ocean for extended periods before attacking, making them impossible to intercept during the boost phase. Most importantly, they could carry multiple warheads and attack numerous targets during a single mission. The concept gained momentum as engineers recognized that nuclear ramjet technology might actually be simpler than traditional reactor designs. Ramjets eliminated the need for complex turbine machinery, reducing the number of components that could fail under extreme conditions. The high-temperature operation actually improved reactor efficiency, making the entire system more practical than initially believed. As 1956 drew to a close, the United States Air Force made the fateful decision to pursue this nuclear-powered nightmare. The project would consume enormous resources and push the boundaries of materials science, nuclear engineering, and weapons design. What emerged from these strategic deliberations would challenge every assumption about the nature of warfare itself. Project Pluto's horrifying vision. The Air Force envisioned a weapon that would solve the bomber crisis through radical innovation. Project Pluto would create the Supersonic Low-Altitude Missile, an unmanned nuclear-powered cruise missile that combined the destructive power of an entire bomber squadron with the unstoppable persistence of a guided weapon. By removing the crew entirely, engineers could eliminate the massive radiation shielding that had doomed previous nuclear aircraft programs, dedicating the entire airframe to fuel, propulsion, and weapons. SLAM measured 27 meters in length and weighed 27.5 tons when fully loaded, making it roughly equivalent to 2 railroad locomotives placed end-to-end. The missile's nuclear ramjet engine would propel it at Mach 3 speeds while maintaining flight altitudes as low as 150 meters above the terrain. This combination of speed and altitude would allow the weapon to approach targets completely undetected by existing radar systems, which were optimized for high-altitude threats. The nuclear propulsion system promised capabilities that conventional missiles could never achieve. Where chemical rockets burned their fuel in minutes, the nuclear ramjet could operate continuously for several days. The Tory 2C reactor design consumed approximately 1% of its uranium fuel per day, allowing extended patrol missions that would keep enemy planners guessing about attack timing and targets. The reactor would generate over 500 megawatts of power while maintaining internal temperatures exceeding 2,500 degrees Fahrenheit. This tremendous heat would be channeled through the ramjet engine, creating thrust by superheating incoming air and expelling it at tremendous velocities. Mission profiles called for SLAM to launch from the continental United States and fly predetermined routes over the Pacific Ocean, circling in international waters until receiving attack orders. The missile could cover distances exceeding 182,000 kilometers without refueling, creating an airborne deterrent force that enemy nations could neither locate nor eliminate through preemptive strikes. Multiple SLAMs could patrol simultaneously, maintaining constant pressure on potential adversaries. The terrain-following flight profile represented a revolutionary approach to penetrating enemy defenses. SLAM would navigate using an advanced system that compared onboard radar readings to stored topographical maps, allowing it to fly at consistent altitudes above ground level regardless of terrain variations. The missile would skim over mountains, follow river valleys, and weave between hills while maintaining its supersonic speed. This flight pattern would keep it below radar coverage until the final moments before impact. The payload capacity distinguished SLAM from every other weapon system conceived during the Cold War era. The missile could carry up to 26 separate thermonuclear warheads, each with a yield of 10 megatons. These weapons would be ejected vertically from the missile's fuselage as it overflew target areas, allowing a single SLAM to destroy dozens of cities during one mission. The total destructive potential represented more than 5,000 times the combined yield of the atomic bombs dropped on Hiroshima and Nagasaki. The weapon's secondary effects proved equally terrifying. SLAM would leave a trail of radioactive contamination along its entire flight path as the nuclear engine expelled fission products through its exhaust. The reactor operated without biological shielding, meaning that radioactive particles would stream from the missile throughout its mission. Communities beneath the flight path would receive radiation doses equivalent to standing near an unshielded nuclear reactor for extended periods. The superheated shock wave created by supersonic flight at such low altitudes would cause widespread destruction independent of the nuclear payload. The missile's passage would announce its presence through a continuous trail of devastation even before reaching its primary targets, as the intense heat and pressure waves scorched everything in its path. Military planners recognized that SLAM represented a new category of psychological warfare. The weapon's ability to loiter over enemy territory for extended periods would create unprecedented terror among hostile populations. Unlike ballistic missiles that provided only minutes of warning, SLAM could circle overhead for days, creating sustained panic and forcing enemy leaders to evacuate population centers repeatedly. The mere knowledge that such weapons existed would fundamentally alter the strategic calculations of potential adversaries. The technical challenges required to make this nightmare operational pushed the boundaries of existing science and engineering. The nuclear reactor had to operate reliably at temperatures that would melt conventional materials while withstanding the extreme vibrations and stresses of supersonic flight. The ramjet engine needed to function continuously for days without maintenance while processing enormous volumes of air contaminated with radioactive particles. The guidance system required innovations in terrain-following navigation that wouldn't become standard in military aircraft for another 2 decades. SLAM needed to process radar data in real time, compare it to stored maps, and make navigation adjustments while traveling at 3 times the speed of sound. The electronic components had to function reliably in the intense radiation environment created by the nuclear reactor. Perhaps most challenging was the warhead deployment system. The missile needed to accurately deliver nuclear weapons to multiple targets while maintaining its own flight path. Each warhead required its own guidance system and parachute deployment mechanism, adding complexity and weight to an already demanding design. Despite these formidable obstacles, the project received official approval and substantial funding in 1957. The Air Force committed to a multi-year development program that would employ thousands of scientists and engineers. The Lawrence Livermore National Laboratory assumed responsibility for reactor development, bringing together some of the most accomplished nuclear engineers in the United States. These experts would soon discover that turning Project Pluto's vision into reality would require solving problems that seemed to violate the fundamental laws of physics and material science. The impossible engineering challenge. Dr. Theodore Merkel and his team at Lawrence Livermore National Laboratory confronted 10 major research and development areas that had to be solved simultaneously to produce a working nuclear ramjet engine. Previous attempts at nuclear-powered aircraft had failed spectacularly, not because the reactors wouldn't work, but because the shielding needed to protect human crews weighed as much as the intended bomb loads. the aircraft nuclear propulsion program had spent over $1 billion trying to solve this fundamental problem, producing aircraft that were too heavy to carry meaningful payloads. SLAM eliminated the crew protection problem entirely by removing humans from the equation. Without pilots or navigators aboard, engineers could eliminate the massive lead and concrete shielding that had doomed earlier projects. This breakthrough freed up thousands of pounds of weight capacity for fuel, weapons, and propulsion systems. However, removing the crew created entirely new challenges that pushed the boundaries of materials science and nuclear engineering into uncharted territory. The operating environment inside a nuclear ramjet exceeded anything previously attempted in reactor design. The engine would generate internal temperatures reaching 2,000 degrees Celsius, hot enough to melt steel and most conventional aerospace materials. These extreme temperatures were necessary to heat incoming air to the velocities required for ramjet propulsion. Intense radiation fields created additional material stresses that conventional engineering couldn't address. The reactor would produce both neutron and gamma radiation at levels far exceeding those found in stationary power reactors, gradually altering the atomic structure of surrounding materials and causing them to become brittle without warning. The supersonic airflow through the ramjet created mechanical stresses that compounded the thermal and radiation challenges. Air entering the engine inlet would be compressed and heated to temperatures exceeding 1,000 degrees Celsius before reaching the reactor core. This superheated air would flow through the reactor at velocities approaching 300 meters per second, creating tremendous pressure, differentials, and vibration loads throughout the engine structure. These extreme conditions exceeded the operational limits of every known material. Steel would melt at the required operating temperatures. Aluminum would vaporize almost instantly. Even exotic aerospace alloys like Inconel and Hastelloy would fail within hours under such conditions. The project required materials that could maintain structural integrity while simultaneously resisting thermal shock, radiation damage, and mechanical stress. The solution emerged from a fundamental redesign of the propulsion concept itself. Rather than adapting existing turbojet technology, Merkel's team chose to develop a nuclear ramjet engine that eliminated most moving parts. Traditional turbojet engines relied on complex compressor and turbine assemblies with thousands of precisely machined components. These mechanical systems would fail immediately under the extreme conditions required for nuclear propulsion. Ramjets offered a simpler approach that matched the unique requirements of nuclear power, containing no compressors, turbines, or other rotating machinery. Instead, they relied on the forward motion of the aircraft to compress incoming air through carefully shaped inlet ducts. The reactor core breakthrough required 465,000 hexagonal fuel elements made from beryllium oxide mixed with uranium oxide enriched to 93.2% uranium-235. Engineers added zirconia and yttria for stability, creating a ceramic fuel mixture that could withstand the extreme operating environment. The beryllium oxide served as a neutron moderator capable of surviving temperatures exceeding 2,000 degrees Celsius, according to Livermore reports. Each fuel element measured 7.5 millimeters across its hexagonal cross-section with a 7.5 millimeter diameter hole through its center, designed to pack closely together in a honeycomb pattern while allowing adequate airflow. The core's porcelain company, better known for producing beer bottles and ceramic fermentation equipment, became the unlikely partner responsible for manufacturing these fuel elements. The production process involved mixing sinterable beryllium oxide powder with oralloy uranyl nitrate, yttrium nitrate, and zirconium nitrate to form a slurry. This mixture had to be carefully controlled to prevent accidental criticality during manufacturing, requiring specialized machinery that could detect dangerous neutron flux levels and immediately halt production if criticality appeared imminent. The fuel elements were supported by a framework of metal tie rods made from Rene 41 and Hastelloy R235 alloys, designed to operate at temperatures up to 760 degrees Celsius while maintaining sufficient strength to hold the reactor core together under extreme aerodynamic loads. Ceramic guard tubes surrounded the tie rods to provide additional structural support and thermal insulation. SLAM's Airframe Design reflected the radical nature of its propulsion system. The missile resembled a wingless flying crowbar with a rectangular cross-section optimized for housing the nuclear reactor and payload bay. The design eliminated traditional aircraft features like wings and vertical stabilizers, relying instead on small control surfaces and the inherent stability of its high-speed flight profile. The streamlined fuselage measured 27 meters in length and incorporated air intakes at the front to feed the ramjet engine, with the reactor positioned amidships and the payload bay extending toward the rear. By 1960, 3 years after the project's inception, the first prototype reactor was ready for testing. The combination of innovative materials, radical design concepts, and manufacturing breakthroughs had transformed an impossible engineering challenge into a working nuclear engine. However, testing this revolutionary propulsion system would require constructing the most elaborate and dangerous experimental facility ever built. Jackass Flats, building a nuclear test site. The Nevada test site already hosted some of the most dangerous experiments in human history, but Site 401 at Jackass Flats would push those boundaries even further. Engineers needed to create a facility capable of testing nuclear reactors under conditions that had never been attempted anywhere on Earth. The remote desert location provided the isolation necessary for experiments that could contaminate hundreds of square kilometers if something went wrong. The compressed air system required for testing represented an engineering marvel that dwarfed most industrial facilities. Nuclear ramjets needed enormous volumes of high-pressure air to simulate the conditions of supersonic flight. Engineers designed a storage system using 40 kilometers of welded oil, well casing to contain 540,000 kilograms of compressed air at 25,000 kilopascals. This pressure exceeded the operating limits of most industrial equipment and required specialized welding techniques to prevent catastrophic failures. 3 massive compressors borrowed from the naval submarine base New London in Groton, Connecticut, provided the power to pressurize this enormous system. These units had originally been designed to test submarine hulls under extreme depth pressures. Each compressor weighed several tons and consumed enough electricity to power a small town. The compressors required 5 full days of continuous operation to pressurize the system for a single 5-minute test run. The heating system pushed industrial technology to its absolute limits. Air flowing through the nuclear reactor would reach temperatures exceeding 1,350 degrees Fahrenheit during actual flight operations. The solution involved 14 million steel balls, each measuring 2.5 centimeters in diameter, contained within 4 massive steel tanks. These steel balls would be heated to 730 degrees Celsius using conventional furnaces before each test. The compressed air would flow over the superheated balls, reaching temperatures comparable to those inside an operating nuclear reactor. Building 2201 served as the nerve center for reactor assembly and disassembly operations. The structure featured concrete walls ranging from 1.8 to 2.4 meters thick to provide radiation shielding equivalent to a nuclear power plant containment building. The building's design incorporated viewing windows made from lead glass measuring 1.2 meters in thickness, allowing technicians to observe reactor operations while remaining protected from deadly radiation. Remote manipulation systems eliminated the need for human contact with radioactive materials. Robotic arms controlled from shielded operator stations could perform precise assembly and disassembly tasks on reactor components. Hot cells adjacent to the main disassembly bay provided additional workspace for handling the most dangerous reactor components, featuring their own remote manipulators and viewing systems for materials that would deliver fatal radiation doses within seconds of direct exposure. The railroad system that connected the test site earned the nickname Jackass and Western Railroad from the engineers who operated it. This specialized railway transported reactor components between the assembly building and the test stands using locomotives specifically designed for handling radioactive cargo. The remotely controlled electric locomotive L-1 served as the primary transport vehicle, operated by technicians safely positioned in shielded control rooms hundreds of meters away from the radioactive cargo. The backup locomotive L-2 featured radiation shielding around its cab to protect a human operator in case remote control systems failed. The shielding added several tons to the locomotive's weight, but provided essential safety margins for emergency operations. Both locomotives could handle the substantial weight of reactor assemblies while maintaining the precision needed for exact positioning at test stands. Underground fallout shelters provided emergency protection for personnel in case of accidental reactor releases. These shelters featured filtered air systems capable of removing radioactive particles from incoming air using multiple stages of filtration, including high-efficiency particulate air filters and activated carbon beds designed to trap radioactive gases. The facility's emergency systems included radiation detection equipment positioned throughout the site. These monitors provided continuous surveillance of radiation levels and could trigger automatic evacuation procedures if dangerous conditions developed. Weather monitoring systems tracked atmospheric conditions that could affect radioactive releases during testing, with wind patterns and temperature inversions determining when test operations could proceed safely. The construction cost reached $12 million, equivalent to approximately $90 million in today's currency. This enormous expenditure covered specialized equipment and construction techniques that had never been used for any other project. Security measures at the site exceeded those of most military installations, with guards maintaining constant patrols while access roads were monitored by electronic surveillance systems. The completed facility would soon prove its worth through a series of increasingly powerful reactor tests. The Tory 2A ground runs in 1961 successfully demonstrated that nuclear ramjet technology could achieve 46 megawatts of power, proving the concept worked. By May 1964, the more advanced Tory 2C reactor reached 461 megawatts for 292 seconds during full power runs, demonstrating that nuclear-powered flight was not just theoretical but achievable reality. The massive infrastructure, advanced robotics, and comprehensive safety systems created a facility capable of bringing the theoretical SLAM concept closer to operational reality. Everything was now in place for the most dangerous experiments in aviation history. The only question remaining was whether the nuclear ramjet reactors would actually work when the moment of truth arrived. The moment of truth arrived on October 14, 1960, when engineers attempted to bring the Tory 2A reactor to life for the first time. The device measured just one-third the diameter of the planned operational engine, a deliberate reduction designed to accelerate testing schedules while proving the fundamental nuclear ramjet concept. The reactor core contained uranium fuel elements surrounded by a thick graphite neutron reflector configured to achieve criticality with the reduced fuel load. Initial startup attempts using regular water coolant failed completely. The reactor refused to achieve criticality despite repeated adjustments to control vanes and fuel positioning. Neutron detection instruments showed frustratingly low readings, indicating that the nuclear chain reaction was not self-sustaining. These failures threatened to derail the entire program before the first test could demonstrate basic feasibility. The breakthrough came when engineers replaced the light water coolant with heavy water, which contained deuterium atoms instead of ordinary hydrogen. Heavy water absorbed fewer neutrons than regular water, allowing more neutrons to participate in the fission process. This substitution finally allowed the reactor to achieve criticality, but only after rotating the control vanes to 65 degrees, indicating that the fuel load remained barely adequate for sustained operation. Early tests revealed various mechanical problems that required iterative engineering solutions. Equipment failures and system malfunctions plagued the initial testing program, but engineers methodically addressed each issue through careful analysis and design modifications. Temperature measurement presented particular challenges because conventional thermocouples would burn up within seconds of reactor operation. Engineer Richard Vierer developed an innovative solution that involved filming the operating reactor and comparing the footage to a temperature-calibrated color scale, allowing accurate temperature readings despite extreme conditions that destroyed conventional instrumentation. The accumulated knowledge from months of preparation, failed attempts, and systematic problem-solving provided the foundation for the critical test scheduled for May 14, 1961. Engineers had refined their procedures, improved their equipment, and addressed the most obvious failure modes through painful experience. The team understood that this test would either validate years of theoretical work or force them to reconsider the entire nuclear ramjet concept. When operators opened the valves on the compressed air tank farm, the nuclear ramjet roared to life with a sound unlike anything heard before in the Nevada desert. The reactor operated for several seconds at 46 megawatts while reaching a maximum core temperature of 1,420 degrees Celsius. Test instruments recorded data that proved the nuclear ramjet principle was not only feasible, but could generate substantial power output under controlled conditions. The successful test triggered an extraordinary celebration that reflected the enormous pressure and dedication of the engineering team. Ted Merkel and his colleagues felt profound relief as their creation first roared to life, validating months of theoretical calculations and engineering modifications. The engineers understood that they had crossed a threshold that transformed nuclear-powered flight from theoretical possibility into demonstrated reality. 3 additional full-power runs conducted on September 28th, October 5th, and October 6th reached maximum power levels of 144, 166, and 162 megawatts respectively. These tests confirmed that the nuclear ramjet could operate reliably at power levels approaching those required for operational weapon systems. The sustained operation at these power levels proved that the reactor design was fundamentally sound and could serve as the foundation for larger, more powerful engines. Following completion of the test series, Tory 2A was dismantled for detailed inspection of its internal components. Engineers examined fuel elements, structural materials, and cooling systems to understand how they had performed under the extreme conditions of nuclear ramjet operation. This analysis provided essential data for designing the next generation of reactors that would push power levels even higher. The fuel elements showed minimal degradation despite exposure to intense neutron radiation and extreme temperatures. The graphite reflector maintained its structural integrity throughout the testing program. Control mechanisms functioned reliably under conditions that would destroy conventional aircraft engines within minutes. These findings confirmed that the basic materials and design approaches were suitable for operational applications. The reactor housing and support structures demonstrated adequate strength to contain the nuclear reactions while withstanding the mechanical stresses of high pressure. Airflow. Cooling systems maintained proper temperature control throughout the test runs, preventing dangerous overheating that could lead to reactor damage or uncontrolled nuclear reactions. The successful operation of all major systems validated the integrated design approach. The success of Tory 2A convinced the Pluto team to skip the planned intermediate Tory 2B design and proceed directly to a full-scale prototype designated Tory 2C. This decision reflected confidence in the nuclear ramjet concept and recognition that the fundamental engineering challenges had been largely solved. The proof-of-concept phase was complete, demonstrating that nuclear-powered cruise missiles were achievable rather than merely theoretical. However, proving the concept represented only the first step toward creating an operational weapon system. The next phase would require scaling up the reactor design to generate power levels sufficient for propelling the actual SLAM missile at operational speeds and altitudes. This engineering leap would dwarf every previous achievement in nuclear propulsion technology. Tory 2C, the full-scale monster. The engineering team now faced the challenge of scaling up their proven concept to operational dimensions. Tory 2C represented the transition from laboratory curiosity to operational weapon system, with reactor specifications that pushed materials science and nuclear engineering into entirely uncharted territory. The new reactor would demonstrate whether nuclear ramjet technology could generate the power levels required to propel a weapon of mass destruction across intercontinental distances. Tory 2C scaled up to 600 megawatts thermal output with 60 kilograms of weapons-grade uranium-235, promising days of flight per Merkel's estimates of roughly 1 gram of fuel consumed per day of operation. The reactor measured 2.6 meters in length and 1.45 meters in diameter, making it roughly the size of a small automobile. This enormous increase from the Tory 2-8 prototype reflected the power requirements for operational flight missions, with the reactor core alone weighing several tons and containing enough radioactive material to contaminate vast areas if released into the environment. The fuel loading represented a quantum leap in complexity and danger. The reactor contained 465,000 individual fuel elements compared to the much smaller number used in the prototype. These elements were arranged in a precise geometric pattern that would maintain criticality while allowing adequate airflow for propulsion and cooling. The power density reached 350 megawatts per cubic meter, concentrating more nuclear energy in a smaller space than any previous reactor design. The construction phase stretched over 16 months as engineers addressed countless technical challenges that had not been apparent in the smaller prototype. The reactor components required specialized handling procedures to prevent accidental criticality during assembly. Workers used remote manipulation equipment to position fuel elements while maintaining safe distances from the growing accumulation of radioactive materials. The assembly process resembled a complex three-dimensional puzzle where every piece had to fit perfectly to ensure proper nuclear characteristics. The comprehensive checkout program involved 82 separate tests over 16 months that confirmed air supply systems, control rod mechanisms, and temperature instrumentation under simulated flight conditions. Each test revealed new problems that required engineering solutions, from mechanical failures in support equipment to unexpected radiation levels in areas previously thought to be safe. The exhaustive testing program reflected the extreme dangers associated with operating a nuclear reactor under conditions that had never been attempted. One significant reactor scram incident during preliminary testing threatened to derail the entire program when safety systems automatically shut down the reactor due to unexpected temperature spikes. Engineers quickly identified the problem as a calibration error in the monitoring equipment and implemented swift fixes that actually improved overall system reliability. These incidents demonstrated the narrow margin between success and catastrophe while highlighting the robust safety systems built into the reactor design. The subcritical tests conducted in early 1964 validated the reactor's nuclear characteristics without generating significant power. These tests confirmed that the control rod systems could maintain reactor stability and that the fuel loading would achieve criticality when brought to full power. The hot zero power tests on April 9th and 23rd simulated full power conditions using electrically heated air instead of nuclear heat, allowing engineers to test airflow patterns and structural integrity without the risks associated with reactor operation. The climactic full power test on May 20th, 1964 represented the culmination of nearly 7 years of development work. Dozens of military observers from the Air Force and Atomic Energy Commission gathered at the Nevada test site to witness what would either vindicate the nuclear ramjet concept or demonstrate its fundamental impossibility. The test represented a moment of truth for engineers who had dedicated their careers to making nuclear-powered flight a reality. The reactor performed beyond expectations during the 292-second test run. The core temperature peaked at 1,242 degrees Celsius while processing 754 kilograms of air per second. The power output reached 461 megawatts, proving that nuclear ramjet technology could generate the energy levels required for operational weapon systems. Observers recorded sound levels that exceeded anything previously heard at the test site, a testament to the enormous forces unleashed by nuclear propulsion. A follow-up test conducted 1 week later pushed performance even higher. The reactor generated 513 megawatts of power while producing 1,560 kilograms of thrust. This thrust level approached the requirements for propelling SLAM at its design speed of Mach 3. The successful demonstration proved that nuclear ramjet technology was not merely feasible, but capable of meeting the performance specifications established for operational weapons. The test data confirmed that nuclear-powered cruise missiles represented a viable weapons technology. The reactor had operated reliably under extreme conditions while generating power levels sufficient for intercontinental flight missions. The nuclear ramjet concept had transitioned from theoretical possibility to demonstrated reality, opening the door to weapons systems that could fundamentally alter the strategic balance between superpowers. The successful operation of Tory 2C validated the most challenging aspect of the SLAM program, but the nuclear engine represented only one component of an extraordinarily complex weapon system. The reactor's proven capabilities now had to be integrated with equally sophisticated airframe and guidance technologies that would transform the stationary test article into a flying weapon of unprecedented destructive power. The flying crowbar takes shape. The airframe development presented engineering challenges that matched the complexity of the nuclear propulsion system itself. Ling Temco-Vought Corporation in Dallas, Texas, received the contract to develop a vehicle capable of sustained Mach 3 flight at sea level, conditions that no aircraft had ever attempted to survive for extended periods. The combination of extreme speed and low altitude created aerodynamic and thermal stresses that exceeded the operating envelope of every existing aircraft design. Dense air at low altitudes created tremendous friction as the missile pushed through the atmosphere at 3 times the speed of sound. This friction would heat the missile's skin to temperatures approaching 650 degrees Celsius, hot enough to weaken most aerospace materials. The heating effects would be sustained throughout the entire flight profile, unlike high-altitude supersonic aircraft that experienced brief temperature spikes during acceleration phases. The wind tunnel testing program required to validate the airframe design consumed 1,600 hours of facility time across multiple laboratories. These tests examined every aspect of the missile's aerodynamic behavior, from basic stability characteristics to complex interactions between the airframe and the nuclear engine's exhaust flow. The testing revealed that conventional aircraft configurations would be torn apart by the extreme forces generated during low-altitude supersonic flight. The final configuration that emerged from this exhaustive testing program defied conventional aircraft design principles. SLAM measured 27 meters in length and weighed 27.5 metric tons when fully loaded, creating a wingless needle-shaped vehicle that engineers dubbed the Flying Crowbar. The absence of wings eliminated the structural weaknesses that plagued conventional supersonic aircraft while reducing the overall complexity of the airframe. 3 fins at the rear provided stability and control, while small canards on the nose allowed precise steering during the terminal attack phase. The structural materials required for this extreme operating environment pushed metallurgy beyond existing capabilities. Vought engineers selected Rene A41 alloy panels for the primary airframe structure, a nickel-chromium superalloy originally developed for gas turbine engines. These panels measured several centimeters thick to provide adequate strength margins under the extreme thermal and mechanical loads. The construction techniques resembled those used for missile airframes rather than traditional aircraft, with thick alloy panels welded together using specialized techniques that prevented thermal distortion. The guidance system represented one of the most sophisticated navigation technologies ever developed for military applications. The Turcom system would navigate by comparing radar readings of terrain features to stored digital maps, allowing the missile to follow predetermined flight paths with exceptional accuracy. This terrain-following capability would enable SLAM to fly at consistent altitudes above ground level while weaving between hills and mountains to avoid radar detection. The system operated independently of ground-based navigation aids, making it difficult for enemies to jam or mislead the missile during its approach to target areas. The electronic systems required for SLAM's operation faced unprecedented challenges from the intense radiation environment created by the nuclear engine. Every electronic component had to be carefully selected, modified, or designed from scratch to survive radiation levels that would instantly destroy conventional electronics. The Air Force operated specialized radiation chambers where potential components underwent rigorous testing under simulated nuclear reactor conditions. Many commercial electronic parts failed within seconds of exposure to these radiation fields, forcing engineers to develop radiation-hardened alternatives using specialized materials and manufacturing techniques. The missile's computer systems used magnetic core memory technology that could withstand radiation exposure far better than semiconductor-based alternatives. These systems stored the terrain maps and navigation algorithms required for autonomous flight operations. The computers processed radar data in real time, comparing incoming information to stored references and making navigation adjustments automatically. This processing had to occur while the missile traveled at supersonic speeds, requiring computational capabilities that pushed the boundaries of 1960s technology. The Warhead deployment system incorporated vertical ejection mechanisms that would launch nuclear weapons upward from missiles' fuselage. This design allowed SLAM to escape the blast effects of its own weapons, enabling the missile to continue operating after delivering warheads to multiple targets. The ejection system used small solid rocket motors to accelerate warheads clear of the missile's flight path before deploying parachutes for precision delivery. The timing and sequencing of these operations had to be precisely coordinated to prevent warheads from interfering with each other or damaging the missile. The primary deployment concept relied on ground-based launch from hardened concrete shelters that would protect the missile from enemy attacks while providing launch facilities similar to those used for ballistic missiles. Solid rocket boosters would accelerate SLAM to the minimum speed necessary for nuclear ramjet operation, burning for approximately 30 seconds to bring the missile to Mach 2.5 before separating and allowing the nuclear engine to take over. The transition from rocket to ramjet propulsion represented a critical phase where engine failures could result in mission failure or catastrophic accidents near populated areas. The integration of all these systems created a weapon that represented the pinnacle of 1960s military technology. The nuclear engine, radiation-hardened electronics, advanced guidance systems, and specialized airframe combined to produce a missile capable of missions that no conventional weapon could attempt. However, as engineers celebrated their technical achievements, they remained unaware that their success would soon create problems far more dangerous than any they had solved in the laboratory. The impossible test flight problem. The technical success of Tory 2C created an unexpected crisis that would prove more destructive than any engineering failure. By early 1964, the House Appropriations Committee had grown impatient with the project's theoretical achievements and demanded concrete proof that SLAM could actually function as an operational weapon system. Committee members issued an ultimatum that would haunt project leaders for months: present a viable flight test program by July 1, 1964, or face immediate budget cuts that would terminate the entire program. The flight test requirement exposed fundamental problems that engineers had avoided confronting during the reactor development phase. SLAM represented the most dangerous weapons test ever contemplated, combining nuclear propulsion with supersonic flight over distances that could span entire continents. The missile would spew radioactive contamination along its entire flight path while generating shock waves capable of destroying buildings and killing people on the ground. No test range in the United States could safely accommodate such a weapon. Testing over Nevada was immediately rejected due to the catastrophic consequences of a potential crash. The missile contained enough radioactive material to contaminate thousands of square kilometers if it impacted populated areas. The nuclear engine would continue operating until the moment of impact, spreading radioactive particles across a vast area that would remain uninhabitable for decades. Even a successful test would contaminate the flight path with radioactive exhaust, creating environmental damage that extended far beyond the test site boundaries. The weight of the fully loaded missile compounded the crash risk scenario. At 27.5 metric tons, SLAM would impact the ground with kinetic energy equivalent to a substantial conventional bomb, even without considering the nuclear materials aboard. The reactor core would likely rupture on impact, dispersing uranium fuel elements across the crash site. Recovery operations would be impossible due to the intense radiation fields, leaving contaminated debris scattered across the impact zone indefinitely. The only viable testing option involved flights over the South Pacific Ocean, where the missiles would follow predetermined routes before crashing into deep ocean trenches at the end of each test. This approach would allow realistic flight testing while minimizing the risk to populated areas. The missiles would launch from Johnston Island or similar Pacific territories, fly extended missions over international waters, then dive into ocean depths exceeding 6,000 meters where recovery would be impossible. The Pacific testing plan triggered immediate resistance from the Atomic Energy Commission, which balked at the environmental consequences of deliberately dumping radioactive materials into the ocean. Each test would release reactor components containing weapons-grade uranium into marine ecosystems that supported commercial fishing and naval operations. The long-term effects of such contamination remained unknown, but Commission members feared that radioactive materials could enter the food chain and affect human populations across the Pacific region. Environmental concerns extended beyond the crash sites to include the entire flight path over international waters. The nuclear ramjet would continuously emit radioactive particles throughout its mission, creating a trail of contamination that would persist for years after the test flights. Ocean currents would distribute these materials across vast areas, making it impossible to predict or control the ultimate extent of environmental damage. Even testing far from populated land masses posed unacceptable risks, as radioactive fallout would spread across ocean currents that connected to fishing grounds and coastal areas throughout the Pacific Basin. NATO allies expressed growing alarm about the missile's operational characteristics, particularly the devastating shock wave that would accompany its flight over populated areas. The missile's 150 decibel noise signature exceeded the pain threshold by significant margins and could cause permanent hearing damage to people on the ground. This sound level was comparable to standing next to a Saturn V rocket during launch, but the slam noise would be sustained throughout the entire flight rather than lasting only a few minutes. The shock wave effects went far beyond noise pollution. Supersonic flight at 150 meters altitude would generate overpressure waves capable of shattering windows, collapsing weak structures, and causing panic among civilian populations. The missile's passage would create a continuous zone of destruction along its flight path, turning the weapon into a terror device that caused massive civilian casualties independent of its nuclear payload. Allied governments calculated that SLAM missions to the Soviet Union would necessarily overfly NATO countries, subjecting friendly populations to the missile's destructive shockwaves. The diplomatic implications of deliberately causing civilian casualties in allied nations created political obstacles that proved insurmountable. European leaders refused to accept the collateral damage that would result from SLAM operations, effectively eliminating most potential flight paths to Soviet targets. The July 1st deadline approached with project leaders unable to present any testing program that addressed the fundamental safety and environmental concerns. The House Appropriations Committee had demanded proof that SLAM could function as advertised, but the weapon's own capabilities made such proof impossible to obtain safely. Environmental objections from the Atomic Energy Commission and diplomatic resistance from NATO allies killed SLAM's testing viability before any flight could be attempted. Congressional appropriators responded by cutting test funding, recognizing that a weapon system that could not be safely tested would never become operationally viable. The testing dilemma highlighted the broader problems with nuclear-powered weapons that extended far beyond technical feasibility. The environmental consequences, diplomatic complications, and safety risks created obstacles that no amount of engineering excellence could overcome. While engineers had successfully proven that nuclear ramjets could work, they had simultaneously discovered that the strategic environment was changing in ways that would make their achievement. The ballistic missile revolution was already rewriting the rules of nuclear warfare. The Atlas Intercontinental Ballistic Missile Program achieved its first successful test launch in 1957, just as Project Pluto was receiving its initial funding. These early Atlas missiles suffered from reliability problems and required hours of preparation before launch, making them seem inferior to the proposed SLAM system. However, the rapid pace of ballistic missile development soon eliminated these disadvantages. The Atlas D became operational in 1959, capable of delivering a 1.4 megaton warhead across 14,000 kilometers in just 30 minutes. This represented a fundamental shift in nuclear strategy from the hours-long missions envisioned for SLAM to near-instantaneous strikes that gave enemies no time to respond. The Titan II program pushed ballistic missile capabilities even further beyond SLAM's reach. These massive missiles could deliver 9 megaton warheads across intercontinental distances while stored in hardened underground silos that provided protection from enemy attacks. The Titan II used storable liquid propellants that eliminated the lengthy preparation times required by earlier missiles. Launch crews could fire these weapons within minutes of receiving orders, making them far more responsive than any cruise missile system. The missile's speed and trajectory made interception essentially impossible using existing defensive technologies. The Minuteman program represented the ultimate vindication of the ballistic missile approach. These solid-fuel missiles could launch within seconds of receiving orders and required minimal maintenance compared to the complex nuclear-powered systems proposed for SLAM. The Minuteman I became operational in 1962, delivering 1.2 megaton warheads with accuracy sufficient to destroy hardened military targets. The missile's simplicity and reliability made it ideal for mass production and deployment in numbers that would overwhelm any defensive system. The accuracy improvements achieved by ballistic missiles eliminated one of SLAM's primary advantages. Early ICBMs could reliably hit targets within several kilometers of their aim points, making them suitable for destroying cities, but inadequate for attacking military installations. However, improved guidance systems rapidly reduced these circular error probabilities to hundreds of meters, then to tens of meters. This accuracy eliminated the need for SLAM's ability to deliver multiple warheads to closely spaced targets, since single ballistic missiles could now destroy individual military installations with precision strikes. The Navy's Polaris submarine-launched ballistic missile program created a sea-based deterrent that rendered SLAM's loitering capabilities obsolete. The first Polaris submarines became operational in 1961, carrying 16 missiles that could deliver nuclear warheads across ranges exceeding 2,000 kilometers. These submarines could remain submerged for months while positioning themselves within striking distance of enemy targets. The mobility and stealth of submarine-launched missiles provided far better survivability than any land-based system, including the nuclear-powered cruise missiles that SLAM represented. The Polaris program demonstrated that ballistic missiles could be deployed on mobile platforms that were essentially immune to preemptive attack. Soviet anti-submarine warfare capabilities remained primitive compared to their air defense systems, making submarine-launched missiles far more likely to reach their targets than any aircraft-delivered weapon. The strategic implications were profound. The United States could maintain a credible nuclear deterrent without relying on vulnerable land-based systems or complex nuclear-powered aircraft. Soviet air defense improvements during this period made the low-altitude cruise missile breakthrough moot by 1964. The SA-2 guideline surface-to-air missile system deployed throughout the Soviet Union could engage targets at speeds exceeding Mach 3, while airborne early warning systems eliminated the advantage of low-altitude flight that had been central to SLAM's design. Even supersonic cruise missiles would face systematic interception throughout their flight profiles. Critics within the Pentagon began referring to SLAM as slow, low, and messy compared to the clean efficiency of ballistic missiles. The nuclear-powered cruise missile required complex support systems, extensive maintenance, and elaborate safety procedures that made it far more expensive to operate than solid-fuel ballistic missiles. The radioactive contamination caused by the nuclear engine created environmental and political problems that ballistic missiles avoided entirely. The complicated flight profiles required for terrain-following navigation made SLAM missions far more complex than the simple ballistic trajectories of ICBMs. The cost-benefit analysis that had once favored nuclear-powered cruise missiles now tilted decisively toward ballistic missiles. The SLAM program had already consumed over $260 million without producing an operational weapon, while a single Minuteman missile cost approximately $7 million, including its silo. The Pentagon could deploy dozens of ballistic missiles for the cost of developing and testing a single nuclear-powered cruise missile. This economic reality made continued investment in SLAM increasingly difficult to justify. The weapon that had been designed to be unstoppable was now demonstrably slower and more vulnerable than the alternatives. SLAM's 3-hour flight time to Soviet targets provided ample opportunity for defensive systems to respond, while ballistic missiles arrived in 30 minutes or less. The cruise missile's complex flight path made it vulnerable to interception throughout its mission, while ballistic missiles spent most of their flight time above the atmosphere where no defensive systems could reach them. The advantages that had made SLAM seem essential in 1956 had become fatal weaknesses by 1964. As the strategic landscape shifted beneath their feet, the engineers who had dedicated years to perfecting nuclear ramjet technology found themselves defending a project that politicians and military leaders increasingly viewed as an expensive anachronism. The technical triumph of Tory 2C had proven that nuclear-powered flight was possible, but the changing nature of warfare had made their achievement strategically irrelevant. The stage was set for a final confrontation that would determine whether Project Pluto would survive into the operational phase or join the graveyard of abandoned weapons programs. Death of a Doomsday Dream. The House Appropriations Committee delivered the death blow to Project Pluto on July 1, 1964, during the summer budget hearings. Committee members had grown increasingly frustrated with the project's inability to demonstrate practical flight testing capabilities and questioned whether the enormous expenditures could be justified given the rapid advancement of ballistic missile technology. The committee's final decision slashed the program's budget to just $1 million for decommissioning activities, effectively terminating all research and development work. This budget reduction represented far more than a simple funding cut. The remaining $1 million barely covered the costs of safely dismantling the test facilities and disposing of radioactive materials that had accumulated during 7 years of reactor development. The committee's action made it impossible to continue pursuing the technical advances that might have made SLAM operational, reflecting a fundamental shift in congressional priorities toward proven technologies that could be deployed immediately. Ted Merkel made one final attempt to save the program during his testimony before the committee. He emphasized that SLAM was 100% feasible and argued that the technical challenges had been solved through the successful operation of Tory 2C. Merkel pointed out that the nuclear ramjet technology had been proven beyond doubt and that the remaining work involved engineering refinements rather than fundamental research. He estimated that SLAM could become operational by the end of the decade if adequate funding continued, but his arguments failed to convince committee members who had already concluded that ballistic missiles offered superior capabilities at lower costs. The project's termination created a bittersweet atmosphere among the engineers and scientists who had dedicated years of their careers to making nuclear-powered flight a reality. Merkel organized a farewell dinner at a local country club where project participants gathered to commemorate their achievements and mourn the end of their ambitious undertaking. The event featured commemorative Thai tacks and bottles of Pluto mineral water as souvenirs, tangible reminders of a project that had pushed the boundaries of nuclear technology further than any previous effort. The dinner reflected the complex emotions surrounding the project's cancellation. Many participants felt genuine relief that they would no longer be working on a weapon designed to spread radioactive contamination across vast areas while delivering unprecedented destructive power. However, The relief was tempered by professional disappointment at seeing years of innovative work terminated before reaching fruition. Chemist William Moran, who oversaw the production of the ceramic fuel elements, later reflected that working on Project Pluto represented the best 6 years of my life. Engineer Chuck Barrett, who directed the Tory tests at Jackass Flats, captured the project's appeal when he stated, "I was young. We had lots of money. It was very exciting." The project employed approximately 350 people at Lawrence Livermore National Laboratory and 100 at the Nevada test site during its peak years. These individuals represented some of the most accomplished nuclear engineers, materials scientists, and weapons designers in the United States. The sudden termination of their work created professional disruption as team members sought new assignments within the nuclear weapons complex or transitioned to other fields entirely. The Tory 2C reactor remained at Jackass Flats for 12 years after the project's termination, serving as a radioactive monument to the nuclear-powered flight concept. The reactor was too contaminated to be moved safely and too dangerous to be left unattended, creating a maintenance burden that persisted long after the program's official end. In 1976, the reactor was finally dismantled at the Engine Maintenance, Assembly, and Disassembly Building, where specialized equipment could handle the highly radioactive components safely. Building 2201 continued serving classified nuclear projects until 2013, when it was finally demolished. The total expenditure on Project Pluto reached approximately $260 million, equivalent to $2 billion in today's currency. This enormous investment produced a wealth of technical knowledge and several prototype reactors, but never resulted in an operational weapon system. The cost per unit of military capability compared unfavorably to ballistic missiles, which could be produced and deployed at a fraction of the expense required for nuclear-powered cruise missiles. The engineers involved in Project Pluto gradually dispersed to other assignments within the nuclear weapons complex, carrying with them specialized knowledge that would influence subsequent programs. The materials science advances developed for SLAM found applications in reactor design, aerospace engineering, and electronics manufacturing. The Turcom guidance system concepts eventually appeared in conventional cruise missiles, while radiation-hardened electronics became standard components in military and space applications. The project's cancellation created a false sense of security that the nuclear-powered missile concept had been permanently abandoned. The technical feasibility demonstrated by Tory 2C proved that such weapons could be built, even if political and economic considerations made them impractical during the 1960s. The knowledge gained from Project Pluto would not disappear with the program's termination, but would remain available for future applications under different circumstances. The nightmare that American engineers had reluctantly abandoned would not remain buried forever. Russia's nuclear ghost returns. The concept that American engineers had abandoned in 1964 erupted back into reality on August 8, 2019, when a massive explosion rocked the Nyanoxa missile testing facility on Russia's White Sea coast. The blast killed at least 7 people and sent radiation levels spiking across the surrounding region, forcing Russian authorities to evacuate nearby villages and close shipping lanes. The official explanation from Rosatom, Russia's nuclear energy agency, mentioned only a radiological accident during testing of a nuclear isotope power source, but intelligence analysts quickly identified the true cause of the disaster. The explosion occurred during testing of Russia's 9M730 Burevestnik missile, known in the West as the Storm Petrel. This weapon represented a direct descendant of the SLAM concept, incorporating nuclear-powered propulsion to achieve virtually unlimited range and endurance. The Burevestnik shared the same fundamental design philosophy as its American predecessor, using a nuclear reactor to heat air for ramjet propulsion while carrying nuclear warheads across intercontinental distances. The accident at Nyanoxa demonstrated that the technical challenges that had plagued Project Pluto remained unsolved 60 years after SLAM's cancellation. Vladimir Putin announced the Burevestnik's development during his 2018 State of the Nation address, describing it as an invincible missile capable of evading all existing defensive systems. Putin's presentation included animated graphics showing the missile circumnavigating the globe while approaching targets from unexpected directions. The Russian president claimed that the weapon's nuclear propulsion system gave it virtually unlimited range, allowing it to remain airborne indefinitely while searching for openings in enemy defenses. This announcement marked the first public acknowledgement that nuclear-powered cruise missiles had returned to active development. The strategic logic driving Russia to revive this Cold War concept reflects the changing global balance of power and the limitations of conventional ballistic missiles. American missile defense systems have improved significantly since the 1960s, creating uncertainties about the penetration capabilities of traditional ICBMs. The Burevestnik's ability to fly unpredictable flight paths at low altitudes potentially offers advantages over ballistic missiles that follow predictable trajectories. The weapon's extreme range would allow Russia to attack targets anywhere in the world without requiring forward-deployed assets or overflight rights from neutral countries. However, the revival of nuclear-powered cruise missiles has generated skepticism among Western analysts. Greg Herr-Ken, an emeritus professor of American diplomatic history, notes that Russia reviving Cold War-era weapons concepts suggests that the Burevestnik may be more propaganda than practical weapon system. The technical challenges that doomed SLAM remain largely unchanged, while the environmental and safety risks have become even less acceptable in the modern era. The Nyanoxa accident highlighted these dangers, creating a radioactive cleanup problem that persists years after the explosion. Intelligence assessments suggest that Russian engineers may have recovered research from Project Pluto to accelerate their own development program. The fundamental physics of nuclear ramjet propulsion remain unchanged since the 1960s, and the technical solutions pioneered by American engineers would provide valuable insights for modern attempts at nuclear-powered flight. The concept of deploying multiple warheads from a single cruise missile, demonstrated in SLAM's 26 warhead design, appears to have influenced Russian thinking about the Burevestnik's potential capabilities. The current global hypersonic weapons race involves the United States, Russia, and China pursuing advanced delivery systems that could fundamentally alter strategic nuclear calculations. These weapons travel at speeds exceeding Mach 5 while following unpredictable flight paths that make interception extremely difficult. Russia has already deployed the Avangard hypersonic glide vehicle and the Kinzhal air-launched hypersonic missile, while China has fielded the DFZF hypersonic glide vehicle. The United States is developing several hypersonic systems, including the AGM-183 air-launched rapid response weapon and the Common Hypersonic Glide Body. Modern guidance and materials technology could make nuclear-powered missiles more viable than their 1960s predecessors. The Turcom terrain-following navigation system pioneered for SLAM has evolved into sophisticated GPS-denied navigation capabilities using terrain correlation and other advanced techniques. Radiation-hardened electronics have improved dramatically, allowing complex computer systems to operate in the intense radiation environment of nuclear reactors. Advanced materials science has produced alloys and ceramics that can withstand extreme temperatures while maintaining structural integrity under severe mechanical stresses. The geopolitical tensions driving current weapons development mirror those of the 1960s arms race in disturbing ways. The bipolar Cold War confrontation has evolved into a multipolar competition involving the United States, Russia, and China, each seeking strategic advantages through advanced weapon systems. The current period exhibits the same combination of technological competition, strategic uncertainty, and escalating rhetoric that characterized the early Cold War years when SLAM was conceived. Nuclear doctrine has also evolved to emphasize flexibility and escalation control rather than massive retaliation. Russia's nuclear strategy includes provisions for limited nuclear use to de-escalate conflicts, while the United States has developed low-yield nuclear weapons for similar purposes. China is rapidly expanding its nuclear arsenal while maintaining an official no-first-use policy. These doctrinal changes create incentives for weapon systems that can deliver precise, variable-yield nuclear strikes while maintaining plausible deniability. The Burevestnik program demonstrates that SLAM's technical viability and enduring terror value continue to attract military planners seeking asymmetric advantages. The combination of unlimited range, unpredictable flight paths, and psychological warfare effects remains compelling despite obvious drawbacks. The weapon's ability to loiter over enemy territory for extended periods creates unique deterrent effects that ballistic missiles cannot match, while its radioactive exhaust trail serves as both a strategic capability and a terror weapon that would contaminate vast areas long before reaching its primary targets. The nightmare scenario that seemed safely buried in 1964 has returned in a world where nuclear competition defines great power relations and technological boundaries continue to expand. The engineers who celebrated SLAM's cancellation in 1964 believed they had buried a nightmare forever. They were wrong. The Burevestnik missile proves that nuclear-powered cruise missiles have returned in an era where great power competition mirrors Cold War tensions. Today's multipolar arms race involves hypersonic weapons, expanding nuclear arsenals, and renewed strategic uncertainty between the United States, Russia, and China. The same technological ambitions that drove SLAM's development now fuel modern weapons programs that push the boundaries of destruction even further. American hypersonic programs like the AGM-183 air-launched rapid response weapon carry forward SLAM's legacy of pursuing seemingly impossible military capabilities. If SLAM once seemed madness, what limits are we willing to toe in the next arms race?